Hello chemists, this is Ms. Placino and you're watching lesson 12.2 on acid and base definitions. Today we're really just going to talk about a couple different ways that you can define acids and bases. Goals for today's lesson include being able to classify acids and bases using the Arrhenius definition, classify those same substances using the Bronsted-Lowry definitions. These are really the two important ones for today. And we're also going to talk about amphoteric substances and their behavior. All right, let's get started. We're going to look at the Arrhenius definition of acids and bases first. If you talked about acids and bases in a middle school science class or really any previous science class, there's a good chance that they were defined using Arrhenius definitions. Any substance that's going to release H+ ions in solution is considered an acid, according to this definition. So if we were to take HCl, dissolve it in water, make it an aqueous solution, we're going to produce hydrogen ions and chloride ions. And it's really this presence of the aqueous H+ ions that make this an acidic substance. You might also see the same sort of dissociation equation written like this, where we have HCl with water present on the reactant side, and we're forming this H3O+ ion, which is the hydronium ion, and the chloride ion again. Make a note that those two notations, whether they're aqueous hydrogens or aqueous hydronium ions, they are the same thing. It's really this presence of an H+ ion floating around in solution, and that's what has led the solution to be acidic. If you think about water, looks like that. When it becomes hydronium, it's because it's been able to kind of snag just an H+ ion that's been floating around. It's going to form that bond, and then this whole polyatomic ion will have a positive charge. But don't be tripped up when you see H3O+. It is still representative of an acid. Arrhenius bases are going to be substances that release hydroxide ions in solution, so our OH- ions. So we've got sodium hydroxide, we dissolve it in water. We know sodium hydroxide is ionic, therefore it's going to split apart or dissociate into its ions. We'll produce a sodium ion in this case, and the hydroxide ion. There really isn't any other way to represent this, like water can't gain an hydroxide ion the way it can a hydrogen. So this is the dissociation equation to be familiar with. All right, let's try out some practice problems. In the previous lesson, we talked a little bit about classifying acids and bases when you go to name them. See if you can remember those rules and apply it to these 6 substances. Is it an acid? Is it a base? Be able to support your answer. So pause the video, figure that out, and unpause it when you're ready to check your work. All right, let's take a look at these. H2SO4, acid or base? Well, you've got those lead hydrogens, so this is an acid. You might even be able to name it, since we did go over naming in the previous lesson. That is sulfuric acid. What about the next one, HNO3? Again, you've got those lead hydrogens. Highly likely that this is an acid. Its name is nitric acid. That's a pretty ridiculous name for a base. The third one, Ca parentheses OH2. We've got hydroxide ions present. Good chance that this is a base. This is calcium hydroxide. Right. The fourth one, HBr. Again, got those lead hydrogens. So this is an acid. This is hydrobromic acid. Fifth one, KOH. Again, we see the hydroxide ions will be produced when this dissolves in water, making this a base. It's potassium hydroxide. And NH3. We got those, my guess is most of us looked at this and said, oh, we've got hydrogens present, high likelihood this is an acid. If you were to take a solution of ammonia and test its pH, it would turn litmus paper blue. This is a base. And at first glance, that might seem insane. We know that bases release hydroxide ions. There's no hydroxide present in NH3 in ammonia. So how is it possibly leading to a basic pH? Really, what we're being shown here is that we have to update our definitions of acids and bases. Simply looking for things that produce H+ and OH- ions is not going to really cover every substance that behaves as a base. So we're going to have to update our definition to what's called the Bronsted-Lowry. And we'll come back and we'll explain in more detail why ammonia is in fact a base. So with our Bronsted-Lowry definitions, it's not a matter of just looking for an ion that's going to be produced. Bronsted-Lowry definitions have to do with protons being passed back and forth between two substances. So we've got some really high-tech drawing here. We got an acid saying, here, have a proton, and the base saying, gee, thanks, as it accepts that proton. So the Bronsted-Lowry definition looks at acids and bases as proton donors and receptors. So an acid is any species that can donate a proton. And again, that's really just another way of saying an H+ ion. So we'll say acids are proton donors. A base is any species that can accept a proton, so it can take that H+ ion, and we call them proton acceptors. So essentially, the definition of acid has not changed really from the Arrhenius to the Bronsted-Lowry definition, but bases have. So if we go back to our ammonia example, and this is something we'll cover in more detail in a future lesson, so if you're a little confused, don't stress. We have NH3. We're going to dissolve it in water. So we'll also have H2O molecules floating around in our mixture. In this case, water is behaving as an acid. It's able to donate one of those protons, one of those hydrogens, to ammonia. So you can kind of think of like that lone pair almost like stealing the hydrogen away from water. As that happens, whoops, waste a little bit more than I meant to, we'll end up creating NH4 with a plus charge. Oxygen's going to hold on to those pair of electrons. And it's going to have a minus charge. Look at what's produced when hydrogen loses a proton. We're left with a hydroxide ion. We know that when hydroxide is in solution, we end up with a substance that behaves as a base. It's going to have like a high pH, for example. So our Bronsted-Lowry bases still end up producing hydroxide. They just kind of do it in this like roundabout fashion, usually by deprotonating water. All right, so let's see if we can define these next half dozen substances using the Bronsted-Lowry definition, or just simply Bronsted definition. All right, so we've got these 6 substances. We know in order to be classified as an acid, we have to have protons to donate. Bases have to be proton acceptors. All right, so kind of given those 2 pieces of information, see if you can make predictions about whether the species listed are going to behave as acids or bases, and be able to, kind of support your answer. Pause the video, try them out. All right, so we have SO3 2-. This is the sulfite ion. There are no protons to donate. There's not a single hydrogen present in that formula, so this has to be a base. Oftentimes, bases are going to have a negative charge. For our Bronsted-Lowry definition, that's usually a good sign that they're able to accept a proton. Up next, HNO2. Ooh, we do have hydrogens present. They're up at the front of the formula, so this is a high likelihood that this is going to be an acid. This is nitrous acid. CH3COOH. Put a star next to this one in your notes. This is kind of a question that students get tripped up on. A lot of students see that OH at the end, and this looks really tempting to call it a base. Bases release hydroxide ions. You might be thinking, wait, we're talking about Bronsted-Lowry bases right now, so is it a proton acceptor? I don't know if I can really tell. This is acetic acid. You probably have this at home. It's the active ingredient in vinegar. This is a donatable proton, and it's not listed up at the front of the formula. This is something called a condensed molecular formula. When we talk about organic chemistry, we'll find that COOH is indicative of a carboxylic acid. Don't get tripped up with this one. New York State loves to try to fool students with that. They also like to try to fool you with this. CH3OH, another substance that looks really tempting to call a base. This is methanol, which is just a type of alcohol. We'll be covering that in organic chemistry as well. So to get back to the problem itself, acetic acid is, of course, an acid. The fourth one, NO3-, the nitrate ion, we don't have any protons to donate, so this must be a base. H3P, I see those hydrogens up at the front. Those are donatable, so I've got an acid. HCO3-. Well, that minus sign makes me think that this could be a base. But I also have that lead hydrogen, which makes me think this could be an acid. This is an example of what we call an amphoteric substance. It can behave as both an acid and a base. So really, whatever you wrote down for this, as long as you didn't leave it blank, you were at the very least were half correct. Let's delve into amphoteric substances a little bit deeper. Amphoteric substances are going to be able to behave as both a Bronsted-Lowry acid or a base, and a base. It really just depends on the environment. That means they're going to be able to both donate and accept a proton. HCO3-, this is the hydrogen carbonate ion, and you actually have this in your bloodstream, and it's supposed to act as a buffer to keep your blood pH from changing too dramatically. You can imagine that, you want to have a pretty stable blood pH, and if it got too far out of whack, too acidic or too basic, that could spell out some really dangerous health problems for you. So if there's additional H+ ions floating around in solution, hydrogen carbonate is going to be able to behave as a base, as a proton acceptor, and kind of grab onto those spare hydrogens and create H2CO3. If there starts to be too few hydrogen ions in solution, hydrogen carbonate can donate a H+ ion, a proton, and form the carbonate ion. So in this direction, we're acting as a base, as H+ ions are being accepted, and it's kind of like almost reverse reaction, the one that's going to the left. This is where hydrogen carbonate is behaving as an acid, and it is donating the H+ ions and forming the carbonate ion. So again, kind of two key things to look for when it comes to amphoteric substances are that negative sign, often suggesting that it can accept a proton, and hydrogen, which if it's at the front or like the first element listed in a formula, there's a good chance that that is a donatable proton. There is one substance that doesn't have these two characteristics but is amphoteric that I'd like you to be aware of, and it's water. Water is able to accept a proton, behave like a base, and become H3O+. Water is also able to behave as an acid and donate a proton, kind of like what we saw with ammonia stealing a proton from water, and then it can form the OH ion. That kind of wraps it up for today. Just be really familiar with those two different definitions of acids and bases. They're going to come up again and again as we talk about acids and bases and we look at reactions between those two types of substances. All right, thank you for tuning in, and I hope you found this helpful.